Hi everybody, today I am going to uh, select the lightest W section to carry a uniformly distributed dead load of 0.5 kg per feet. This is the superimposed dead load, that is in addition to the beam weight, and we are given the live load of 0.9 kg per feet. The simply supported span of the beam is 20 feet. So the compression flange of beam is fully supported against lateral moment. So we are not doing anything with the lateral torsional buckling, but we are the given section is fully supported against lateral moment. So now we are told to select the lightest beam for A36 and A99 steel. So now let's solve this problem and select the lightest section. Solution. This is too thick. Let me make it small. Solution. Let's say this is question number 1 for now. This is number 1. Right. Now we are given dead load. WD is equals to 0.5 kg per feet, and the live load is 0.9 kg per feet. It is superimposed dead load, so we are not including the beam self-weight. It's already included in the question. So now the length of the beam is equals to 20 feet. Alright, so now we are solving this problem using load and resistance factor design. So let me write this. We are solving this problem using LRFD solution. Our solution, we're doing LRFD solutions. So now let's calculate the ultimate load. So W is equals to, so this ultimate load for LRFD load combination is given in AISC 710. So you can use AISC 710 manual. So 1.2 WD plus 1.6 WL governs this equation, this solution. So it's 1.2 WD is 0.5 kg per feet plus 1.6 live load is 0.9 kg per feet. So solving this, we will get the ultimate load of 2.04 kg per feet. And now let's calculate the ultimate moment. We know that this is a simply supported beam. Let's draw a beam before we calculate a moment. So also let me draw a beam here. This is a hinge and roller on the other end. So this is simply supported beam with ultimate load of 2.04 kg per feet, and the span of beam is 20 feet. So the maximum, so our bending moment diagram is gonna be like this. So this is our maximum moment, which is W L square divided by 8. So for ultimate load, our maximum moment is mu is equals to W L square by 8, which is equals to 2.04 kg per feet, 20 feet square divided by 8, which will give us the maximum moment of 102 feet cube. So let me verify this one more time before. 2.04 times 20 square by 8, which is equals to 102 feet cube. So now now we know the maximum moment that this beam can withstand is the plastic moment, so which is MP. So phi b nominal moment is equals to phi b and plastic moment, right, which is equals to phi b Fy and Zx, plastic section modulus. So now we know that the value of phi b for the flexural member is 0.9. It's given in AISC Civil Construction Manual. So now the design requirement is required Zx, right? We have to find the plastic section modulus. So we know that ultimate moment mu is equals to phi b Fy Zx. So from here we can find the value of Zx, ultimate moment divided by phi b Fy, which is equals to, so our ultimate moment is 102 feet cube, which is 102 feet cube divided by the resistance factor is 0.9. Yield stress, so we are solving for grade A36 steel, so let me write for A36 steel. So the yield stress of A36 steel yield strength is 36 KSI. So we have KSI in the bottom, we have feet cubes, so we're gonna change this unit to inches, so 12 inch per 1 feet, which gives us the plastic section modulus of 37.78 inch cube. Now using this plastic section modulus value, we can go to the AISC Steel Construction Manual. I have AISC's 14th edition. So when you go to the table 3-2 on AISC Steel Construction Manual, so let's look for the let's select the section from here. So it's 37, so I'm going to go to the back of the face, 37.78. so let's select W14 by 26. So we can say this select from AISC Manual table 3-2. So try W14 divided by 26 with plastic section modulus of 40.2 inch cube. So this is the more economical section. You can see other section W10 by 33, W8 by 40, but see the bold W section, that's the lightest and economical section. So now after selecting the section, so we will check the compactness of the section, whether the flange is compact, flanges and the wave are in compact or not. So classification, now our next step is classification of section for local buckling. Classification of sections for local buckling. So you can see this on section B 4.1. So classification section for local buckling, we do this for both the flanges and the web. So classification of flange and flexure, classification of flanges in flexure, which is in table B 4.1b of AISC Manual case 10. So this thing is in AISC Manual. So when you go to this section, you can see that. So let me go to the W by T thickness ratio. So if it's 14th edition steel construction manual, then you can see this on page number 16.1-17. So width to thickness ratio, which is BF to so when you see in this manual, so BF, so the width B is half the width of that flange, so BF divided by 2 times thickness of flange. That's what we do it here. So now for W 14 by 26 section, let's find out the value of width of flange and the thickness of flange, which is W 14 by 26, W 14 by 26, W 14 by 26. So W 14 by 26, so in serves a slander for comparison with Fy equals to 50 KSI 14 by 26. Let's try how well we're gonna get 5.03. So 5.03. So thickness of twice thickness of flange is 0.335. This gives us 7.51. Right now limiting ratio for compact section. So limiting ratio for compact section and limiting ratio for non-compact section, let's find out the value. So it's case number 10 of this manual. So we can also call this as lambda. So limiting ratio for compact section, which is lambda P flange and flexure 0.38 under root E over Fy, which is 0.38. Modulus of elasticity of steel is 29,000 KSI. Yield stress of steel is 36 KSI. Solving, we get 0.38 times under 29,000 KSI divided 36, which is 10.79. Okay, limiting ratio for non-compact section which is lambda r, planes in flexure, which is 1.0 under root E over Fy, 1.0, 29,000 KSI divided by 36 KSI. So this gives us 28.38. So this section is compact. Now classification of wave in flexure. Now let's check for the wave. Classification of wave in flexure, same table, B 4.1. so this is case number 15, AISC Manual, right? So width to thickness ratio is given by thickness of wave. So the height is equals to depth minus 2 depth minus 2k thickness of wave. So we're gonna find the depth of this. What was our section? 14 by 26. 14 by 26. So this is in table 1-1. Depth is 13.9 minus 2. The value of k is 0.820. So thickness of wave is 0.255. Let me verify it one more time. 26, 14 to 26, 13.9 minus 2k, 0.820 divided by thickness of wave 0.255. So solving this, we will get 13.9 minus 2 times 0.0 divided 0.255. 48.1. Now limiting ratio for compact section. Section is in case 15, compact section. So lambda p wave in flexure is given by 3.76 under root of E over Fy, 3.76. Modulus of elasticity of steel is 29,000 KSI divided by 36 KSI steel, which gives a 3.76 under root of 29,000 divided by 36.72. Limiting ratio for non-compact section. Which is equals to 5.70 under root of E over Fy, 5.70 which is equals to 5.70 29,036 gives us 161.77. Since, let me tell you this, since h over t is less than or equals to 2 of this value, which is lambda pwf, and so this is compact section. So now if this is a compact section, then we will compute the so we are good. Now check the strength. So we're going to check the strength here now. Check strength, correct the factored moment MU to include the beam weight. So this is our final step. This is final step. So check the strength. Correct the factored moment MU to include the beam weight. Alright, so our ultimate load is gonna be 1.2. What was our 0.5? So our 0.5 plus 14 by 26, 26, 14 by 26, 14 by 26. So 26 divided by 1000, which gives us value 0.026. This is kip per feet plus 1.6. What was our live load? It was 0.9 kip per feet. So solving this two, we get 1.2 times 0.5 plus 0.026 plus 1.6 times 0.9, which is equals to 2.07 kip per feet. And now our ultimate moment M ultimate equals to WL squared by 8, which is 2.07 kip per feet times 20 feet square divided by 8, which gives us 2.07 times 20 square by 8, which gives us 103.5 kip per feet. So this is okay. So the nominal moment Mn equals to plastic moment equals to Zx. So let's do this. Let's include the phi also. So including phi b. So phi b Mn equals to phi b Mp equals to phi b Fy Zx. So you can get this value directly from the manual, but we are doing for A36 still. So let's calculate 36 kips per square inch, and Zx. What was our Zx? We calculate our Zx equals to, this is the calculator, 40.2 inch cube, 40.2 inch cube, 40.2 inch cube. This gives us 109, 0.9 times 36 times 40.2 which is equals to, so this is equals to 1302.48 inch cube. Convert it into feet, so when you convert this we can do just 1 feet per 12 inch, right, divided by 12, which we get 8.54 feet cube, which is greater than or also, so our section is okay. So this is our final